So we're going to take a look at another set of functions, only this time we're going to just look for the domain. So for example 5, we're going to find the domain of each of the following functions. The first function, f of x, is equal to x minus 4 over x squared minus 2x minus 15. So this problem, we need to avoid division by 0. So we need to determine where the denominator is 0, which means solving this equation and setting it equal to 0. So we have x squared minus 2x minus 15. We can factor that to be x minus 5 times x plus 3, which is equal to 0. Now solving both of them for x yields x is equal to negative 3 or x is equal to 5. So these are the only values of x that we need to avoid, and so the domain is the following. The domain is all real numbers except x is equal to negative 3 and x is equal to 5. Part B, g of t is equal to the square root of 6 plus t minus t squared. In this case, we need to avoid square roots of negative numbers. And so we need to require that we're going to set what's under the radical to be greater than or equal to 0. Now what we want to do is, we want to make sure that the negative t squared becomes a positive. So if we change all these signs, that means that we need to then flip the inequality. So this inequality now becomes a greater than or equal to becomes less than or equal to, because all of our signs will then change to the following. So now we have t squared minus t minus 6 is less than or equal to 0. Now what did we do to do that? Well, we multiplied the whole inequality by negative 1. And remember, to switch the direction of the inequality, when you multiply by a negative, to make this easier to deal with. You'll need to be able to solve inequalities like this more than a few times in a calculus course, so let's make sure you can solve these. The first thing we need to do is determine where the function is 0, and that's not too difficult in this case. We have t squared minus t minus 6. We're going to factor that to be t minus 3 times t plus 2, which is equal to 0. Now solving for t, the function will be 0 at t is equal to negative 2 and t is equal to 3. Now these points will be the only place where the function may change sign. It's not required to change sign at these points, but these will be the only points where the function can change sign. This means that all we need to do is break up a number line into the 3 regions that avoid these 2 points and test the sign of the function at a single point in each of the regions. If the function is positive at a single point in the region, it will be positive at all points in that region because it doesn't contain any of the points where the function may change sign. We'll have a similar situation if the function is negative for the test point. So here's a number line showing these computations. So noticing what we found here, in our previous example, we had negative 2 and positive 3 are our testing points. And what it's done is it's created 3 regions. So we have region 1, we have region 2, and then we have region 3. Okay, and so in region 1, what we're doing is we're checking the point negative 3, which is what we're plugging into that function. And we want to find out whether it's going to be greater than or less than 0. So if we plug in negative 3, we get 9 plus 3 minus 6, which gives us 6. And therefore, this 6 is greater than 0. In region number 2, we're picking the value to be x is equal to 0. So we're picking 0 in this region. So plugging in for x, we get 0 minus 6, and therefore this is negative 6. That means that this is less than 0 because it's negative 6. And in region 3, we're going to pick the value of 4. So plugging in 4, we get 4 squared, which is 16, minus 4, which is 12, minus 6 gives us positive 6. So therefore, this value 6 is greater than 0. So from this, we can see that the only region in which the quadratic in its modified form will be negative is in the middle region. Recalling that we got to the modified region by multiplying the quadratic by a -1, this means the quadratic under the root will only be positive in the middle region, so the domain for this function is the following. It's in between -2 and 3 inclusive. So therefore, we know that it's true in region 2 and then false for regions 1 and 3. So that means we have a bracket here and we're including everything in between -2 and 3, which then represents our domain. Part C, we have h of x, which is equal to x over the square root of x squared minus 9. In this case, we have a mixture of the two previous parts. We have to worry about division by 0 and square roots of negative numbers. We can cover both issues by requiring that x squared minus 9 must be greater than 0. Note that we need the inequality here to be strictly greater than 0 to avoid the division by 0 issues. We can either solve this by the method from the previous example, or in this case it is easy enough to solve by inspection. The domain in this case is x is less than -3 and x is greater than 3. So we have left parenthesis -infinity comma -3, right parenthesis, and left parenthesis 3 comma infinity right parenthesis.